At 3,800 meters below the surface of the North Atlantic lies the wreck of the Titanic. For most people, that already sounds impossibly deep. At that depth, there is no sunlight. The water is close to freezing, and the pressure is hundreds of times greater than it is at the surface. But if the Titanic were somehow suspended above the deepest point of the ocean, our journey would not even be halfway finished. Below, it would still be almost 7 kilometers of water. That is the scale of the world we are about to enter. A world where sperm whales hunt giant squid in darkness, where animals create their own light, where entire ecosystems survive without energy from the sun, and where small, pale creatures live under pressures capable of destroying machines built from some of the strongest materials humans can manufacture. And eventually, almost 11 kilometers beneath the Pacific, we will reach the Mariana Trench and Challenger Deep, the deepest known point in the ocean. But reaching the bottom immediately would miss the most important part of the story, because the ocean does not suddenly become deep. It changes layer by layer, and with every few hundred meters, the rules of life change with it. At the surface, everything feels familiar. Sunlight penetrates the water. Phytoplankton capture its energy. Small animals feed on them. Fish feed on those animals, and larger predators hunt the fish. Almost every familiar marine food chain begins here. This upper layer is known as the Sunlight Zone. It extends roughly to 200 meters. Coral reefs, schools of fish, sea turtles, sharks, and many marine mammals spend at least part of their lives within this illuminated world. But light is already being filtered from the moment it enters the water. Red disappears first, then orange, then yellow. The deeper we descend, the less of the visible spectrum survives. By about 200 meters, there is no longer enough sunlight to support normal photosynthesis. This is where the ocean begins to separate from the world above. We have entered the Twilight Zone. Between roughly 200 and 1,000 meters, faint light may still arrive from the surface, but it is no longer enough to power an ecosystem. Animals here cannot depend on plants growing around them. They need different strategies. Some are almost transparent, others are silver, reflecting what little light remains, so that predators struggle to see their outline. Some are dark red, a color that appears almost black at depth. And every night, something extraordinary happens. Countless animals rise from this darkness toward the surface to feed. Before daylight returns, they descend again. This enormous daily movement of life is one of the largest animal migrations on Earth, yet almost no human being ever sees it. For us, even this relatively shallow part of the journey is already dangerous. Water pressure increases rapidly as we descend. Human divers have reached extraordinary depths, but doing so requires specialized gases, equipment, and extremely slow ascents. The deeper a diver goes, the more gases can dissolve into the body under pressure. Return too quickly, and those gases can form bubbles in tissues and blood vessels. The result can be decompression sickness, paralysis, or death. That means that, for humans, depth is not simply a question of swimming back upward. Once you enter this world, even escaping it becomes complicated. And at 1,000 meters, our journey reaches another boundary. Look upward now, and there is effectively no daylight left to guide us. Day and night at the surface have become almost meaningless. We are entering the midnight zone, and from this point onward, if something appears in the darkness, it may be because the animal itself wants us to see it. Because down here, life has learned to manufacture light. At around 1,000 meters below the surface, the ocean becomes a world of permanent night. But permanent darkness does not mean total darkness, because many deep-sea creatures carry light inside their own bodies. Bioluminescence is one of the most important adaptations in the deep ocean. Through chemical reactions, living organisms produce flashes, glows, and pulses of light. Some use it to communicate, some use it to hide, some use it to confuse attackers, and others use it to kill. The anglerfish is probably the most famous example. A glowing lure hangs in front of its mouth. In a world where food can be difficult to find, a tiny point of light can be irresistible. A smaller animal approaches. The predator barely has to move. But the anglerfish represents only one solution. Siphonophores can form long, luminous colonies drifting through the water. Some squid use light to break up their silhouette. Tiny fish carry rows of glowing organs along their bodies. And in complete darkness, a single flash may contain information we still do not fully understand. But light is only one problem. The other is food. The deep ocean contains no meadows, no forests, and almost no photosynthesis. So much of its energy must arrive from somewhere else, from above. Every second, tiny fragments of organic material are sinking through the water. Dead plankton, waste, mucus, fragments of animals. Scientists call this slow rain of material marine snow. To us, it might look insignificant. To an animal living thousands of meters down, it can be the difference between feeding and starving. And where food becomes rare, evolution rewards patience. Many deep-sea predators move slowly. They conserve energy. Some have enormous mouths compared with their bodies. Others have stomachs capable of expanding when a rare large meal finally appears. Because in the deep ocean, refusing food simply because it is too large may mean waiting weeks for another opportunity. Around 2,000 meters, however, the darkness also becomes a hunting ground for some of the largest predators alive. Sperm whales regularly dive deep in search of squid. They do not need sunlight to find them. They use powerful echolocation, sending clicks through the water and interpreting the returning echoes. Their prey has evolved a very different solution. Giant and colossal squid possess enormous eyes, allowing them to detect faint movement and approaching predators in near darkness. Scars found on sperm whales and squid remains recovered from their stomachs reveal that these encounters happen again and again. Yet humans have almost never witnessed the actual battle at depth. Think about that. Some of the largest predator-prey encounters occurring anywhere on Earth may be happening every day in an environment we almost never see. And as we continue downward, the pressure keeps increasing. At 3,000 meters, ordinary human physiology is irrelevant. Only specially engineered vehicles can bring us here. Then, at approximately 3,800 meters, something familiar appears in the darkness. The Titanic. The ship rests on the floor of the North Atlantic, broken into sections and slowly being consumed by the deep ocean. Microorganisms interact with its iron. Rust-like formations grow across the wreck. Piece by piece, one of the most famous machines ever built is being returned to the environment around it. But Titanic also gives us an important sense of scale. This feels like the bottom of the world. It is not. The average depth of the global ocean is around 3.7 kilometers, so the Titanic lies close to a depth that is, on the scale of the planet, surprisingly ordinary. The truly extreme ocean begins below it. At 4,000 meters, we cross another invisible boundary. Above us are kilometers of black water. Below us lies a landscape wider than continents, the abyssal world, and here, the deep sea stops feeling like empty water. For the first time, the seafloor becomes the main character. Between roughly 4,000 and 6,000 meters lies the Abyssal Zone. The word abyss makes it sound like a vertical hole. Much of it is nothing like that. Instead, enormous abyssal plains stretch across the ocean floor. Cold, dark, quiet, fine sediment covers the bottom. A sea cucumber may move slowly across the mud. Brittle stars extend thin arms. Crustaceans search for fragments of food. Worms live beneath the sediment, and microbes perform processes that remain invisible to the camera. At first glance, it can look almost empty, but the abyss is not empty. It is an ecosystem operating on a very different budget. Energy arrives slowly. Marine snow continues falling from kilometers above. Occasionally, something much larger arrives, a dead fish, a squid, or, rarely, the body of a whale. When a whale reaches the seafloor, the effect can be enormous. A whale fall can create a temporary island of food in a landscape where large meals are extraordinarily rare. Scavengers arrive first, then smaller organisms, microbes transform what remains. A single body can feed deep-sea communities for years, but the abyss contains places where life does not need to wait for food falling from above. And when humans discovered them, they changed one of our most basic ideas about life on Earth. Hydrothermal vents, cracks in the ocean crust, allow seawater to circulate through hot rock below the seafloor. The water heats up, reacts with minerals, and rises again. When that mineral-rich fluid meets the cold, deep ocean, strange chimney-like structures can form. Black plumes rise into the darkness. Around them, life gathers: tube worms, crustaceans, mollusks, microbes, dense communities living in a place where no sunlight has ever reached them. For a long time, it was easy to imagine that virtually every major ecosystem on Earth ultimately depended on the sun. Plants capture sunlight, animals eat plants, predators eat those animals. Follow the chain backward, and the energy eventually leads to sunlight. Hydrothermal vent communities revealed another possibility: chemosynthesis. Certain microbes can use chemical energy rather than sunlight to produce the organic material that supports an ecosystem. That discovery transformed the deep sea into something larger than a biological curiosity, because if life can thrive in darkness using chemistry, then sunlight may not be essential for life everywhere. That is one reason deep ocean research is connected to the search for life beyond Earth. Icy moons, such as Europa and Enceladus, may contain oceans beneath their surfaces. If energy and suitable chemistry exist there, the deep ocean shows us that darkness alone does not rule life out, and that may be the greatest surprise of the abyss. At first, it appears hostile because we judge it using the rules of the surface: no light, almost freezing water, immense pressure, very little food. But life does not need our conditions. It needs conditions it can adapt to. And below 6,000 meters, that idea becomes even more extreme. The broad abyssal plains begin to give way to something different. Deep trenches cut into the crust of the planet. This is the Hadal Zone. Its name comes from Hades, the ancient Greek underworld. And unlike the broad plains above, Hadal environments exist mainly inside the deepest ocean trenches. Here the pressure becomes extraordinary. The amount of food decreases. Fish become rarer, and yet, life follows us down. The Hadal Zone begins at around 6,000 meters. Only a small fraction of the ocean reaches these depths. Most of it is contained inside trenches created by plate tectonics. The Mariana Trench exists because two enormous sections of Earth's crust meet in the western Pacific. The Pacific Plate moves beneath the Mariana Plate in a process called subduction. Over millions of years, that movement has created a long depression in the seafloor, a scar in the crust stretching for thousands of kilometers. And inside that scar are environments found almost nowhere else on the planet. At these depths, the pressure is hundreds of times greater than at the surface and continues increasing as we descend. Yet small animals move across the sediment as if nothing were unusual, because to them, nothing is unusual. They were built here. One of the most famous examples is the Hadal snailfish. It does not look like an invincible deep-sea predator. Its body is pale, soft, and almost delicate. It lacks the heavy structure we associate with animals built for strength. But that softness is part of the solution. Deep-sea organisms cannot simply build armor against pressure and hope it will hold. Their cells and chemistry must continue functioning while pressure acts through almost every part of the body. Special molecules help protect proteins from distortion. Many deep-sea organisms reduce rigid structures and gas-filled spaces. The result can look fragile at the surface while being perfectly suited to the deep. A Hadal fish brought rapidly upward would not suddenly become stronger in our environment. It could be damaged by the loss of the very conditions that shaped it. Other residents have evolved completely different strategies. Amphipods, shrimp-like crustaceans, scavenge material accumulating inside the trenches. Some Hadal amphipods grow far larger than their shallow water relatives. Xenophyophores take strangeness in another direction. These organisms can form structures visible to the naked eye despite being single-celled, a biological unit operating at a scale that challenges our everyday idea of what a cell should look like. And this is where the mythology of the deep ocean often gets ahead of the science. People imagine that the deepest zone must contain the largest monsters, megalodons, unknown giant sharks, creatures too enormous to approach the surface. But extreme depth does not automatically create giants. Large active predators need enormous amounts of energy. The deepest trenches are cold and food limited. That makes them a difficult place to support enormous, fast-moving hunters. The reality is, in many ways, stranger. The most remarkable animals here are remarkable precisely because they are not monsters. They are small organisms solving impossible biochemical problems. How do you keep proteins working at enormous pressure? How do you find food when almost none is produced around you? How do you reproduce when members of your species may be separated by huge distances? How do you live in a world where sunlight has never existed? And the farther down we travel, the more those questions matter. At 8,000 meters, we are already deeper than almost every mountain on Earth is high. At 9,000 meters, the pressure is approaching 1,000 times surface pressure. At 10,000 meters, very few crewed vehicles in history have ever operated. And somewhere below us lies the point humans spent centuries trying to reach, Challenger Deep. But before we touch the bottom, we need to understand how extraordinary it is that anyone arrived there at all, because the first people to do it were not using 21st century technology. They descended in 1960 inside a steel sphere barely large enough for 2 men, and during the journey, they heard something crack. On January 23, 1960, the bathyscaphe Trieste floated above the Mariana Trench. Inside were Jacques Picard and U.S. Navy officer Don Walsh. Their destination was Challenger Deep. No human being had ever reached it. Trieste looked very different from a conventional submarine. Its crew occupied a small, extremely strong pressure sphere. Above it was a large float filled with a liquid lighter than water. Heavy ballast allowed the vehicle to descend. Release that ballast, and buoyancy could carry the craft back toward the surface. It was an elegant idea, but elegance did not make the journey safe. The descent would take hours, and beneath them was almost 11 kilometers of ocean. They began near the familiar blue surface. Then the sunlight faded. The Twilight Zone disappeared above them. They entered permanent darkness. Thousands of meters passed. There was no window view of some enormous underwater canyon opening dramatically beneath them. Mostly there was black water, depth represented by instruments, pressure represented by what the hull had to survive, and the knowledge that every meter placed more ocean above their heads. Then, near 10,000 meters, they heard a crack. Inside a pressure vessel at that depth, few sounds could be more frightening. If the main sphere failed, there would be no rescue, no emergency ascent, no time to react. The damage turned out not to be catastrophic. Trieste continued. After almost 5 hours of descent, the vehicle finally reached the floor of Challenger Deep, approximately 10.9 kilometers below the surface. For the first time in human history, Two people were sitting at the bottom of the deepest known part of the ocean. Their landing disturbed the sediment. A cloud of fine material rose around the craft. Visibility became poor. They believed they observed small animals and possibly a fish, although later interpretations questioned exactly what they had seen. That uncertainty is almost perfect. Humans had risked everything to reach the deepest point on Earth, and even after arriving, the ocean still refused to show them much. They remained for only around 20 minutes. Then they released ballast and started the long journey back to the surface. For more than half a century, very few people would repeat what they had done. Space became the new frontier. Humans went to the moon. Robotic spacecraft reached other planets. Telescopes looked billions of light years into the universe, and Challenger Deep remained almost untouched. Then, in 2012, filmmaker and explorer James Cameron descended alone in Deep-Sea Challenger. New materials and modern engineering allowed a much smaller vehicle to make the journey faster and remain on the bottom far longer. Later expeditions pushed deep-sea vehicles toward something even more important than record-breaking: repeatability. A vehicle that reaches the bottom once proves something is possible. A vehicle that can return again and again turns a record into science. Modern landers, remotely operated vehicles, and autonomous systems can now carry cameras, collect water, sample sediment, and document animals without placing a human crew inside the most dangerous part of the mission. And every expedition changes the picture. The Mariana Trench is not simply a deep hole. It contains slopes, sediments, microbial communities, volcanic activity, and ecosystems structured by depth, geology, and the movement of organic material near the broader Mariana region. Hydrothermal systems reveal extreme chemistry. At the deepest levels, scavengers and microbes process whatever energy reaches them, and the trench continues collecting evidence of what happens far above, including something no explorer wanted to find. Human pollution, plastic particles, and other contaminants have reached environments so remote that humans can barely reach them themselves, which creates an uncomfortable comparison. Our technology has still explored only tiny pieces of this world directly, but our influence has already arrived. And that brings us to the final question, not how deep the ocean is. We now know that number. The more interesting question is how much of the world hidden inside that depth we actually understand. Challenger Deep lies almost 11 kilometers below the surface of the Pacific Ocean. That number is easy to say. It is much harder to feel. Imagine looking out of the window of a passenger aircraft flying at cruising altitude. Far below are landscapes, roads, mountains, and cities. Now imagine that distance is vertical water. The surface is where the aircraft would be. You are standing on the seafloor. That is roughly the scale separating Challenger Deep from the world above. And every part of that enormous vertical distance can contain a different environment. Near the surface, sunlight creates abundance. At 200 meters, photosynthesis begins to disappear. In the Twilight Zone, animals use darkness as camouflage. By 1,000 meters, natural daylight is gone. Bioluminescent creatures create signals of their own. Farther down, sperm whales search for squid through sound. Marine snow carries energy from the surface into a world that cannot produce enough food for itself. At roughly 3,800 meters, Titanic rests in darkness. Below 4,000 meters, abyssal plains stretch across enormous areas of the planet. Hydrothermal vents demonstrate that ecosystems can exist using chemistry rather than sunlight. And below 6,000 meters, trenches enter the Hadal Zone, where life continues under pressure that can destroy ordinary machines. But the most important thing is what our descent does not reveal. We can describe the layers. We can map the large structures. We can name many of the animals, but a deep-sea camera illuminates only a tiny area at any one moment. Outside that cone of light, the ocean becomes black again. An animal can move past only meters away and never be recorded. A species may occupy one slope, one vent field, or one trench, and remain unknown because nobody has placed a camera there at the right time. And this is why the deep ocean does not need fictional monsters to be mysterious. Reality already gives us enough. Animals built around pressures that would kill us. Fish that use living light. Squid hunted by whales in battles almost no human has seen. Single-celled organisms large enough to notice without a microscope. Microbes powering entire communities with chemical energy, life surviving at the physical edge of where vertebrates can exist, and perhaps thousands of organisms still waiting to be described. Each new deep-sea expedition is not simply visiting another location. It is sampling a world larger than the land we live on, and far less accessible. That matters because human activity is moving downward too. Waste sinks, pollutants travel, fishing reaches deep habitats. Interest in resources on the ocean floor continues to grow, and some deep-sea ecosystems may recover extremely slowly after disturbance. A coral that took centuries to grow can be damaged in seconds. A habitat formed over geological time can be altered before scientists have properly documented what lives there. So our race into the deep has changed. The first explorers wanted to prove humans could reach the bottom. Today, the challenge is different. Can we understand what is there before we change it? The Mariana Trench is the perfect symbol of that problem. It is the deepest known place in the ocean, but depth alone is not what makes it extraordinary. What makes it extraordinary is that after centuries of exploration, after sonar, satellites, submersibles, ROVs, and autonomous robots, the deepest parts of our own planet can still surprise us. For most of human history, the ocean floor was a place imagined rather than observed. Now, for brief moments, our machines can turn on a light there. A snailfish moves across the sediment. An amphipod approaches a lander. A transparent animal drifts through frame. A hydrothermal vent releases mineral-rich water from Earth's crust, and then the vehicle moves away. The light disappears. The darkness returns. Life continues exactly as it did before we arrived, almost 11 kilometers below the surface, far beneath storms, ships, and sunlight, in a world that has existed beside us for millions of years and still remains largely outside ordinary human experience. The deepest ocean is not empty, it is not lifeless, and it is not waiting for imaginary monsters to make it interesting. The truth is more extraordinary. At the bottom of our own planet, life has found ways to exist under conditions that once seemed impossible. And every time we descend, we discover one more reason to wonder what is still moving beyond the reach of the light.